Greetings. We will continue our discussion on the Hartree-Fock self-consistent field method, and the elements of the Slater determinant are the spin orbitals, okay. And I always like to remind that there is no classical analog to the spin part or to the orbital part, and essentially the spin orbital is made up of these wave functions. So, you have got an orbital part which is the coordinate representation of the quantum state vector, and this is the representation of the spin state vector in the spin space. So, you have got the spin part and the orbital part, and together they constitute the spin orbital. The subscript here I represents the quantum state. So, it represents a set of 4 quantum numbers, and the argument q represents the space as well as the spin coordinate. Now, that is a notation we have, and you have the columns which sort of keep track of the coordinates and the rows which keep track of the quantum states which are occupied, and it is a matter of choice. You choose that, okay, these are the states which are occupied. I gave the example of the helium atom, or you take any atom, sodium atom if you like, and you can say that, okay, 1s, 2s, 2p, 3s states are occupied in one configuration, but in the excited state of sodium you have the no electron in the 3s, but it is excited to 3p, right. So, the occupation of 3s would be 0 and the occupation number of 3p would be 1. So, there will be no row corresponding to the 3s in the 11 electron system corresponding to the sodium atom in the excited state. So, that row will be missing, but it will be substituted by the row corresponding to 3p. So, the configurations, the choice of a configuration and the occupations and the choice of the rows is, these are all connected to each other, they are interlinked. Now, there are factorial n ways of permuting these n electrons in n quantum states, and that is what the determinant represents, and you can write this as the permutation operator operating on this direct product of these n particle states and single particle states, okay. These are the elements which appear along the diagonal, and you permute, and every time you permute you pick a sign -1. Every time there is one interchange, each interchange will contribute one change of sign, and depending on the number of interchanges in a permutation, the parity would be either +1 or -1 for that permutation. And there are factorial n permutations, and assuming that each of these single particle states belongs to an orthonormal basis, which is what we will seek, okay. Eventually the single particle states that will go into the Slater determinant will be required to belong to an orthonormal set, and in anticipation of that we can see that the normalization will be 1 over factorial root factorial n. You can easily see this for a 2 electron system, extend it for a 3 electron system, or maybe you, if you do not want to try it out over here, you will do it in the exam, okay. So, this is the n electron wave function. This operator which generates an antisymmetric wave function is what is called as an antisymmetrizer, because that is precisely what it does, it describes the operator very well. And the spin and the orbital angular momentum are defined by the commutation relations as we have learnt in unit 2, and these are the ones which will go into the description of the single particle states. Now, before we have a very extensive discussion on the entire self consistent field method, I will spend some time talking about the smallest many electron system, which is the 2 electron system. So, let us just consider 2 electrons, nothing else. Okay. Our entire system under consideration is just a pair of electrons. These are identical particles, so they will be described by a geminal because they are completely indistinguishable. Okay. So, let us see what kind of quantum states we get which describe this 2 electron system. So, now this is the 2 electron system whose arguments are q1 and q2. q1 is a set of 4 coordinates, q2 is also a set of 4 coordinates. So, actually there are 8 variables sitting in that, right, and this is written as a spin orbital. This is the orbital part, the space part, and this is the spin part. Okay. So, chi zeta 1 zeta 2 is the spin part and phi r1 r2 is the orbital part. Now, if you interchange q1 and q2, okay, so in place of q1 you have q2 and in place of q2 you have q1. This is the original wave function subjected to one interchange. The wave function must change its sign, okay, because these are electron wave functions, right. This is the fermion system. So, this becomes minus of psi q1 q2, but this minus sign can be associated with phi or with chi. Okay. You can have minus phi times plus chi or plus phi times minus chi. There are 2 possibilities and both the possibilities are consistent with the antisymmetry of the wave function, either of them, right. So, the question is which part, space part or the spin part, which is antisymmetric and which is symmetric, because if you have the minus sign over here, it is the space part which is antisymmetric and the spin part which is symmetric. Over here it is the spin part which is antisymmetric and the space part which is symmetric. So, the properties of symmetry and antisymmetry can go either with the space part or with the spin part, but not with both. Now, this has very important consequences. So, this is what we have got, and you have the antisymmetry contained in this minus sign associated either with the orbital part or with the spin part, and these are the 2 possibilities, that phi r2 r1 is equal to plus phi r1 r2. So, phi r2 r1 should be equal to plus phi r1 r2, right, and chi zeta 2 zeta 1 must be equal to minus of chi zeta 1 zeta 2, okay, or you should have phi r2 r1 to be equal to minus of phi r1 r2. So, either the orbital part is symmetric or the spin part is symmetric, but not both. So, what do these 2 possibilities correspond to? They correspond to the spin being either 0 or 1, because the net spin of the 2 electron system is given by this summation of S1 and S2. So, this is a coupling of 2 angular momenta, both of which are half. So, the net spin will go from half minus half modulus, which is 0, to half plus half, which is 1. So, there are 2 possibilities, S being either 0 or 1, and if S is 0, the corresponding m quantum number can be only 0, whereas if S is 1, the corresponding m quantum number will be either minus 1, 0 or 1, because m quantum number goes from minus j to plus j, and j itself goes from modulus of j1 minus j2 to j1 plus j2. So, that is all we have used here. So, accordingly you have either a triplet state with S equal to 1 or a singlet state corresponding to s equal to 0. The names singlet and triplet are self explanatory, because you have got a single state corresponding to this. There is only one m quantum number that you get over here, whereas over here you have 3 possibilities of the m quantum number. So, this is the triplet. So, you have either the singlet or the triplet, and the singlet state will have 0 spin, right, and the triplet state will have either 1 or minus 1. Okay, so, the triplet state will have parallel spins and the singlet will have anti-parallel spins. Okay. Now, this is quite nicely, it describes the singlet state, because chi zeta 2 zeta 1 is equal to minus chi zeta 1 zeta 2, and then if you have zeros on both sides, then 0 is equal to minus 0 even in atomic physics. So, that works out well enough for us, right. The other state is the triplet state. So, you have got a singlet state and a triplet state, and these are the 2 possibilities you get for the geminal wave function. So, now that we have got this, let us ask the question, which will have lower energy? Do they have the same energy? Do they have a different energy? And if it is different, which state will have a lower energy? Now, the energy is determined by the Coulomb repulsion between the 2. Okay. So, you have to examine the Coulomb repulsion. So, these are the singlet and the triplet states. The singlet has got an antisymmetric spin part and the triplet has got an antisymmetric space part. Now, this we know. So, now we examine the Coulomb interaction. Now, can you guess which state would have lower energy? Actually, the form of the wave function which is written on this slide would suggest to you which would have lower energy if you examine it closely. Notice that there is a plus sign here, the orbital part, okay, and this has got a minus sign over here. What it means is that in the limit R2 going to R1, okay, what is going to happen when R2 goes to R1? The 2 particles, the 2 electrons get closer and closer, right. So, as R2 goes to R1, what happens to the triplet state? Phi 1 R1, Phi 2 R2 minus Phi 1 R2, Phi 2 R1, okay, that would go to 0, right. As R2 goes to R1, the space part would vanish, and for the triplet state to exist, R2 would not be too close to R1, it would be farther away from each other than what is required for the singlet state, right. So, the 2 particles, the 2 electrons would tend to be farther away from each other in the triplet state than in the singlet state. And what happens to the Coulomb repulsion energy? It goes as 1 over distance, right. So, now you have a larger distance in the triplet state compared to the singlet state, but this is repulsion, right. So, the triplet will have lower energy compared to the singlet. So, this is very nicely stated in Landau and Lifshitz's book, in which they say that the triplet state is less punished by the Coulomb interaction. It is a nice way of saying it. Okay. So, now the next thing we will discuss is the representation of the Coulomb interaction in the geminal basis set, and you have got a 2-dimensional basis. This is the basis for what? This is the basis for a pair of electrons. Okay, our electron system is a pair of electrons. So, this is a 2 electron 2-dimensional basis set. One corresponds to Phi 1 R1, Phi 2 R2, the other corresponds to the interchange of these 2 particles. Okay. So, that the electron, so this is the measure of the probability amplitude of the electron at coordinate R2 to be in the quantum state Phi 1. Okay. Likewise, this is the probability amplitude that an electron at coordinate r1 is in the quantum state 2. So, these are base functions. This is the first function, this is the second function, and this is the interaction you are looking at. This is the Coulomb interaction, but the 1 over the distance, okay, 1 over rij, and you can look for a matrix representation of the Coulomb interaction in this basis set, and a typical matrix representation is simply given by this integral, right. So, this is what you have to do for the Coulomb interaction, and accordingly you will have a matrix representation of the Coulomb interaction, which will consist of a 2 by 2 matrix u11, u12, u21 and u22. So, these are the integrals that we have to determine. Okay. So, let us look at these integrals now. Let us look at u11. u11 is this integral, which is the integral of the Coulomb interaction, which is 1 over r12 in this phi 1 r1 phi 2 r2 both complex conjugated, and on this side you have got phi 1 r1 phi 2 r2, and you must integrate over r1 and r2. r1 consists of 3 space coordinates, so this is actually a triple integration. Likewise, r2 is also a set of 3 coordinates. They could be x2, y2, z2, or r2, theta 2, phi 2 if you are using the spherical polar coordinates, no matter what, but you must integrate over all the variables over the entire space. So, this integral is u11, and this is often written as the Coulomb integral, written as J. Okay, this is the Coulomb integral. What about u12? u12 is the integral in which you must sandwich the Coulomb operator, which is the 1 over distance operator, between these two states, between the first and the second, right. So, this is phi 1 star r1 phi 2 star r2, but here you have got phi 1 r2, that is the interchanged, right, and this is phi 2 r1, and this is again a double integration, but each integration is an integration over 3 variables. So, this is actually an integration over 6 variables, 6 space variables. So, when I refer to this as a double integration, you have to remember that each is over a set of 3 coordinates. Okay. So, this is the matrix element u12, which you write as k, and this is usually referred to as the exchange integral. So, these are our definitions of the Coulomb integral and the exchange integral, and they will appear in the many electron formalism throughout. What about u21? Develop an expression for u21. So, u21 is this element, right. This is phi 1 star r2 phi 2 star r1, and then you have got phi 1 r1 phi 2 r2 on this side. So, what is it, k star, right. So, this is the complex conjugate of k. Now, what is going to happen if you take the complex conjugate of k star? Take the complex conjugation of every term over here. So, let phi 1 star r2 become phi 1 r2. Now, phi 1 r2 comes here, right, and if you just do it term by term, you find that k star is actually equal to k. Okay. K star, the complex conjugated, is the same thing as k, because integration is over dummy variables. R2 and R1 can be interchanged, those labels can be interchanged, there is nothing big about it. Okay. Whether you carry out integration over R1 or R2, it is the same. So, essentially you have got this matrix form of the Coulomb and exchange integrals, which is j k k star j star, which is the same thing as j, k, k and j, because k star is equal to k, j star is equal to j, both are real. Okay. And this is the usual terminology, although some books refer to these as I and j. So, instead of j and k, some books refer to these as I and j, and then this j corresponds to exchange, whereas this j corresponds to Coulomb. So, depending on what you are reading, you have to be a little careful, but this is just a matter of terminology. One is the Coulomb interaction, the other is the exchange interaction. Whether you label it as j and k or I and j is just a matter of some convention, some choice of different authors, but it is good to be alert to that, because j may represent either the exchange or the Coulomb depending on who you are reading. So, in this basis, the Coulomb interaction is obviously not diagonal, but you can diagonalize it. So, let us do that, go ahead and diagonalize it. So, you find a matrix T which will diagonalize it. So, T u T dagger will give you a diagonal 2 by 2 matrix, and this is a simple problem in matrix diagonalization which you can do in 2 minutes. Okay. So, find the matrix which will diagonalize this matrix of j k k j, and some of you perhaps already have the answer, and the diagonal elements will be respectively half of j minus k plus j, which is j minus k and j plus k. So, these are the diagonal elements, okay, and these will give you the corresponding like eigenvalues of the problem, and the matrix which diagonalizes the matrix j k k j is this 1 over root 2 1 minus 1 1 1. So, this is the matrix which diagonalizes the 2 by 2 Coulomb exchange matrix. Okay. Notice that these two differ, j minus k and j plus k. The difference in the energy would be twice k, and this matrix which diagonalizes this will also transform this basis to a new basis, and you would expect what this new basis would be. You already have the answer, because this new basis, when you operate on the this matrix operate on the basis set. So, phi 1 r 1 phi 2 r 2 and phi 1 r 2 phi 2 r 1 is the basis set, and if you operate on this by this matrix T, which is the one which diagonalizes the Coulomb interaction, you get the singlet and the triplet states as you would expect, right. So, these are the Coulomb and the exchange integrals, and we will be using them very extensively in our discussion. So, the main reason to spend some time on just the 2 electron system and develop these expressions for the Coulomb and the exchange integrals is because our objective in the self consistent field method is to find the variation in the expectation value of the n electron Hamiltonian in the n electron wave function, vary it and seek an extremum. We definitely look for a minimum, but I will explain why you do not, or how you can take into account the second derivative and determine whether it is a maximum or a minimum or a saddle point. So, these points, these are the subtleties of the variational techniques that we can discuss separately. We will do that, but for the time being we know that we are looking for an extremum in the expectation value of the n electron Hamiltonian in the n electron wave function, and this Hamiltonian is made up of either the single particle operators or the 2 particle operators, and this 2 particle operator is the Coulomb interaction, the 1 over r1j or rij, right, and we therefore will need the Coulomb and the exchange integrals in the analysis of this expression. So, it is for this reason that I set up the machinery to handle the Coulomb and the exchange integrals at the outset, and now we look for getting an extremum of this, so that a variation in this would vanish, subject to the constraint that the individual spin orbitals remain orthogonal to each other and normalized. So, the inner product I j is expressed as a Kronecker delta. So, when j is equal to I, it will be equal to 1, that will be the normalization. When j is not equal to I, it would vanish. Okay. Now, what are I and j? These are sets of 4 quantum numbers. Okay. Each is a set of 4 quantum numbers represented by a single label, single symbol, but it is a set of 4 quantum numbers. And the wave functions over here are the Slater determinants. You can represent it using the antisymmetrizer operator. So, the matrix element then consists of psi star omega psi. So, this is psi star, this is omega, and this is psi, right, and you have got factorial n terms on this side and another factorial n terms on this side. So, it is a lot of work. Okay. It is a lot of work, and you are not going to be doing this just for the helium atom, you will do it for neon, you will do it for calcium, iron, silver, mercury. You have got a periodic table, okay, and there are like 100 electrons, and you have got factorial n terms. Okay. It is a lot of work. You do not have enough ink to write all these things, you do not have enough storage space. So, you need some really good tricks to handle this. Okay. So, it is too much work, we are lazy fellows. So, we will figure out how to minimize our work. So, let us look at this expression now. Now, you have got factorial n terms on this side and another factorial n terms on this side. I write the psi star just as it is, as an integral. Okay. This one I write explicitly as the antisymmetrizer operator operating on the product of the diagonal elements in the Slater determinant, which is u alpha 1 q 1, u alpha 2 q 2, u alpha 3 q 3, all the way up to u alpha n q n, right. So, this is the wave function psi, this is the complex conjugate which I write as it is as psi star, but only on this side I write it as a Slater determinant, but not as a Slater determinant in the form in which we use the antisymmetrizer operator, and we know that the two are completely equivalent to each other, right. So, now let us take this expression and see if we can simplify this a little bit, and a whole lot of simplification is possible. In fact, amazing amount of simplification. Now, the summation and the constants and so on can be written over here. Okay. These are the two operators which stay over here, omega p, right. What is omega? Omega in our context is going to be either the single particle operator H1 or the two particle operator H2, and both of these operators do not care whether you are calling this is electron 1 and this is electron 2 or vice versa, right. In other words, omega commutes with the permutation operator, right. So, you can write omega p as p omega, no problem there. Okay. It is because the interaction does not put a name or a number on the electrons, you can permute them any which way and the interaction remains the same. So, omega p becomes p omega, and now let us see if we can move this operator p. We have moved it from the right to the left, and I want to take it all the way to the left outside the integration sign. but then I must worry about what it would do to psi star, because if I am to put the permutation operator behind psi star, I must compensate for it, because the permutation operator, when it operates on the wave function or even the complex conjugate of the wave function, it will give you -1 times p times that wave function, which could be either +1 or -1 depending on the number of interchanges which are involved in that permutation, right. So, you can move it behind this, but you compensate for it by having a p inverse and restrict the effect of p inverse to this bracket. Okay. So, you can take this permutation operator p, write it over here, and you find that this matrix element of omega is now given by this 1 over root factorial n, the permutation operator operating on this summation -1 to the power p is coming already over here. You have integration over all of these n variables. Each variable is a set of 4 variables, mind you. Okay. And you have p inverse psi star omega, and what you have over here is not the Slater determinant, but just the direct product of the diagonal elements in the Slater determinant. So, let me carry this result to the top of the next slide, which is here, is the same relation. Okay. So, you have got a p here, a p inverse over here, and omega over here, and a product of the diagonal elements in the Slater determinant here. And what does p inverse do to psi star? It will give you -1 to the power p, right, and this -1 to the power p together with this -1 to the power p will give you -1 to the power 2 p, and that will always be +1, it does not matter what permutation is, right. So, this -1 to the power 2 p will always be +1. So, you can take it off from your expression, and now you have got this factor 1 over root factorial n, then you must permute the result of whatever is in store over here, and that is an integration over all of these n variables, psi star, omega, and here you no longer have factorial n terms, you have got only one term in place of that factorial n, right. You began with factorial n terms in the operand, but now you have only one term. Now, that is a good bit simplification, right. In fact, it gets better, it gets even better. Let us see how. So, now you have got this expression here. Now, look at this result. What is in this blue box is what you are going to permute, and the result you will add factorial n times. Okay, you are integrating over all of these n variables, and then you permute the indices. How does it matter? They are dummy labels. Okay, q1, q2, everything is a dummy label. I can call q1 as x, q2 as y. Okay, so I can call q1 as q2 and q2 as q1. So, even after you do the interchange, the result of that integral, that multiple integral, will remain invariant, and you have got a quantity which remains invariant under permutation, and you keep adding it to itself how many times? Factorial n times, exactly. So, the result of this summation is factorial n times that integral, and that factorial n comes in the numerator. You have got a root factorial n in the denominator. So, you are left with a root factorial n in the numerator times this multiple integral. So, we have got a lot of simplification now. Look at this integral. This is an integrand which is being integrated over the integration variables, right. What are the integration variables? q1 through qn. what is this permutation operator doing? It is going to permute the states, right. So, it is like evaluating a result which does not depend on this permutation, get a result, permute the labels and then add it to itself, because you must carry out a summation over all the permutations from 1 through factorial n. So, you have got a result that you keep adding to itself factorial n times. So, it is factorial n times the result of that integration. Okay. So, this is what we have got over here, and this is now our net result, that the matrix element of the 1 electron operator or the 2 electron operators, we are going to have to do this for both H1 and H2, or F and G as some authors call it, right. And you can determine this integral separately for H1 and H2, and omega would be either of these two operators, and we will have to work out these expressions for both. So, let us do it for H1. Okay. So, let us do it first for H1, and what is H1? H1 is the sum of the kinetic energy part of each electron plus the potential energy of that electron in the field of the nucleus, the Z over R, okay, or the ZA square over R if you like, right, that is H1. So, this depends on a single coordinate, which is why it is a single particle operator. So, f of q1 is that single particle operator, which is the sum of the kinetic energy part for the ith electron plus the potential energy of that electron in the field of the nucleus, that is f. So, f of q1 qi, I summed over from 1 through n is your operator H1, and you must take its matrix element. On this side, on the operand side, you have got just the direct product of the diagonal elements in this later determinant. Here you have got the entire factorial n terms in this later determinant, right. So, this is your matrix element of H1. Here you have the entire factorial n terms. How do you get those factorial n terms? By allowing the antisymmetrizer operate on the diagonal elements product, but these are complex conjugated. This is how you get the psi star. So, that means that this matrix element of H1 in the n electrons later determinant is now given by this wave function psi star I write over here. This is the operator H1 which is over here, and this is the product of the diagonal elements in this later determinant. Now, let us bring it up to the top of the next slide, which is here, and you recognize the different pieces in the integrand, right. This is the psi star, this is the operator omega which is H1, and this is the diagonal product of diagonal elements in this later determinant. So, this is the integration that we have to analyze. Now, here you have got factorial n permutations, and you know that all the permutations actually form a group, but that is, we do not have to get into that. It will consist of an identity permutation and then the rest of them, right. So, I write the term corresponding to the identity first and then the rest. So, the first term corresponds to the identity. So, for the identity I will have u alpha 1 star q1, u alpha star q2, u alpha star alpha n qn. This is just the complex conjugate of what you have on this side, okay. That is the one which comes from the identity, and then you have got the remaining permutations, and how many are there? There are factorial n minus 1, because the factorial n permutations includes the identity, that is the one which I have explicitly written out, and the remaining terms I have packed together in the second term. So, this pack of the residual factorial n minus 1 terms is what I call as the remainder R. So, I have got a term in the identity permutation plus a remainder. Now, you recognize what the remainder is. Okay? And then what we are going to do is to discover that the remainder actually goes to 0. That will be so nice, is it not? Right? That is what I told you, that it keeps getting better, it really does. Okay? And it is not at all difficult to see that the remainder vanishes. Okay? Let us see how. Let us ask ourselves, what really happens to the remainder? There are so many terms, factorial n minus 1, it is a huge number. Now, let us look at this. So, these are the remaining terms. So, this is the remainder r, which is equal to all of these remaining permutations except the identity, and you have got the operator H1, which contains the single particle operators for all the n electrons. And now what I do is to separate this I equal to 1 through n again into two pieces, one for f of q1 and the other piece for the remaining electrons, which is I equal to 2 to n. Okay? So, I have just split that summation into two parts, one consisting of the operator corresponding to just the electron at q1, and now look at these terms. So, let us have a look at the first term, which is this one, which is the upper one, the remaining corresponds to the other electrons in the operator. So, let us look at this term over here. Now, this has got all the remaining permutations, everything except for the identity, because identity we have already separated out, right. So, we have all the remaining permutation, and the remaining permutations will have at least one interchange, because the identity is the only one which does not have an interchange, and we have already separated that term. So, it will have at least one interchange. So, let us consider the term corresponding to just one interchange, and let us do that for the first term. So, now one interchange will give you, instead of u alpha 1 star q1, it will give you u alpha 1 star q2. Okay? So, I consider the interchange between q1 and q2. Okay? Right? So, this is the interchange. So, I have got u alpha 1 star q2, I have got u alpha 2 star q1. What about u alpha 3 star? The argument will be q3, because there is only one interchange that we are restricting ourselves to, right. U alpha 4 star, it will have, the argument will be q4, right. So, we are not touching the remaining ones, only one interchange. And now you have this multiple integral. What is the integration over? Integration is over q1, q2, q3 up to qn, and these are independent degrees of freedom. So, you can carry out these integrations separately. So, take the integration over q1. What do you have in the integrand? You have got over q1, you have got u alpha 2 star q1, this is the thing which has got argument q1, this operator is f of q1, and this function u alpha 1 q1 is here. What about the remaining terms? Integration over q2 will involve u alpha 1 star q2, and then you will have u alpha 2 q2, but then this integration will vanish, because alpha 1 and alpha 2 are orthogonal states. So, it does not matter what is the value of this integral, you are going to take some number and multiply it by 0. The result is 0 even in atomic physics, right. You cannot help it, right. Now, the same thing is going to happen to the remaining terms. Okay. And if you look at the remaining terms, okay, the whole remainder vanishes for exactly this reason, and the reason is very simple. The whole remainder vanishes because you will have exactly this kind of thing happening from the remaining terms over here. You will be able to factor out one term and then find it being multiplied by an orthogonality integral, which you know at the outset will be 0. So, the remainder vanishes. What does it do to us? That this whole complex expression that we had, which we factored into this and a remainder, we have the remainder going to 0 and we have only this term to work with. That is a lot of simplification now. And here you have integration over n variables. Each integration, each variable is a set of 3 continuous space variables and 1 discrete spin variable, right. So now you can write this as a, you can separate out the integrations over q1, q2 and so on. What does the integration over q2 give you? dq2 u alpha star alpha 2 star 1 q2 u alpha 1 q2. This is the normalization integral. So you will have this integral multiplied by 1 into 1 into 1 into 1 into 1. We know how to do that, right. So what does it give you? You get just this integral over q1, and then you will get similar terms from the remaining electrons, right. So this is the term coming from the electron 1, because that is what we did, we separated the term for electron 1 and then you had the remaining terms, and now from the remaining terms you will have a similar integral. But then what makes it even simpler is that over here the integration variable is a dummy variable, right. So it really does not matter, okay. They are all the same, okay. So you just have to sum over similar terms, and you have got similar terms for the remaining n minus 1 electrons, j going from 2 to n, and you can pack all the terms together, that this is your original expression that you began with, and for omega equal to h1 you pack all of these integrations together and you find that it is just a summation over I going from 1 through n of these single particle integrals, and you do not need to label this as q1 or q2 or q3 or so on, because all of these are dummy labels. Who cares what you call it, right. A rose is still a rose no matter what you call it. So the dummy label q replaces this, and we have now arrived at a very simple expression for the matrix element of the one particle operator. In the next class we will deal with the 2 particle operators, then we will do the 2 together, then seek the condition under which the expectation value of the n electron Hamiltonian in the n electron Slater determinant would vanish, subject to the constraint that the original single particle spin orbitals remain orthogonal to each other and they remain normalized. Okay. So any question for today?
The last part of that remainder going to 0, can you explain that again?
Yeah, let us go back a few slides over here. Yeah, this is the term. So I guess we should begin at the top of the slide here, okay. And over here what we have done is to separate one of the terms, the fq1, and the remaining terms for I, instead of summation going from 1 to n, you let it go from 2 to n. So far so good. And now you have got factorial n minus 1 terms under this summation. This is a summation of all the permutations. In the original Slater determinant you have got factorial n permutations, but we have separated the identity term. It is only after the separation of the identity that we had a remainder at all, okay. So whatever you have under the factorial n minus 1 permutations does not have the identity, and therefore it has at least one interchange. If there are more than one interchanges, it in fact becomes easier, because it goes to 0 for more than one reason, okay. But even if there is a single interchange, it goes to 0, that is the main point. So, let us consider the term for just one interchange, and here I have swapped the states 1 and 2. So, here you have got u alpha 1 star q 2 u alpha star alpha 2 star q 1. So, that is the interchange that I refer to. There is one single interchange. All the other 1 electron states are the same, and now I separate the integration over the different variables which are q 1, q 2 and q 3. So, what is coming under the integration of q 2 is only those functions whose argument is q 2, and the only functions whose argument is q 2 is one is over here u alpha 1 star q 2, and then you will have a u alpha 1 alpha 2 q 2 coming from here, which is sitting in these dots, right. So, there will be the u alpha 2 q 2. So, now look at this integral which is in this red color. This integral is nothing but the orthogonality between alpha 1 and alpha 2, and that vanishes.
So, f of q1 won't act on others because okay they just commute.
Sorry,
That f of q1, that
f of q1 will operate only on those functions whose argument is q1. F of q1, you know precisely what it is. It is a kinetic energy operator for electron 1. So, the gradient operator, which is d by dx, it is actually d by dx1, right, because it is the coordinate of that particular electron. You are looking at the variation with respect to a particular coordinate. So, it is not going to operate, that gradient operator will do nothing to the other wave functions. Okay. So, that is the reason this f of q1 appears only in this integral and in nothing else, and the other integrals involve this. There will be an integration over q3 which will give you unity, because that did not involve any interchange. So, it will give you the corresponding normalization integral, but so what, means you have got a product of a number of factors, one of which is 0, and you are happy enough to throw the whole term without even looking at what else there is, right. So, the moral of the story is that 0 multiplied by anything, any number is 0.
we are not sure about the other integral, right, whether it is goes to perfectly go to infinity then.
No, it does. All the other integrals will have exactly the same kind of factors. It will have one factor involving, yeah,
we are not about, we don't know anything about it. First term, if it
yeah,
is, its integration is perfect, it's not tending to if it blows up then
no, there is no reason for it to generate a singularity, there is no reason for it to blow up. Because these are normalized wave functions, okay, and you are not doing anything crazy to them, okay. So, you do have a point that okay, you might want to worry about, you know, the rest of the integrals of course are unity, so you know precisely what they are, but this one it really does not matter what it is, okay. So, you get a 0 for the remainder, and that really simplifies your expression very much. So, now you find that your net result is what we have at the end, which is here, that the matrix element of the single particle operator is now just the sum of these over these n I going from 1 through n of these single particle integrals, and this is all just a single particle integral. There is just one gradient operator here, there is a potential energy term, okay, and you integrate it over the n 1 electron orbitals. So, in the next class we will deal with the 2 electron part, the H2, and then we will proceed to apply the variational calculus. So, essentially this is the problem now in variational calculus, and this is now you can state it as a variational problem, how to find the extremum of a function subject to certain constraints. Okay. So, you will use the method of Lagrange's method of variational multipliers. Yes, your question.
So when you pulled out the p outside the integral and you left a p inverse inside to a
Yes.
conjugate space, so how did you define the operation p interval? You got a minus sign in the next step. How did you define the operation?
Yeah, because what an operator does to an operand is that it will operate on everything that is there on the in the operand, okay, if it is within its range of operation. And what a permutation operator does is to carry out an interchange either one or more or none if it is an identity permutation, right, but it has the potential to interchange either once or many times. So, when you move the permutation operator from right to left, you have to make sure that whatever it operates on, and it has the potential to operate on everything on its right. Now, we need to do this compensation only in the psi star, not in this part, right. That is the reason I put that term in a bracket, okay, because the range of applicability of that operation is to be restricted to that. And when the permutation operator operates on psi star, it will give you minus 1 to the power p times psi star. So, that is the extra minus 1 to the power p that we got, but then there was minus 1 to the power p already. So, together we got minus 1 to the power 2 p, and then we did not have to worry about whether it was plus 1 or minus 1, because minus 1 to the 2 p is always plus 1, right. Any other question? So, thank you all very much.